Hi there. So I want to talk about what I can potentially offer out here on YouTube. And partly I'm doing these Roblox videos, but I'm also going to be doing sort of math ramblings. And also just teaching math that I know pretty well sometimes. However, so there's these there's deep things in math that not enough people are talking about. And a big reason why not enough people are talking about them is that they are difficult subjects to learn and difficult to teach. And so, for example, Lie theory, all of that stuff, this is not going to be very easy to see, is it? So let me change that. Let's do this. I'm trying to mix it up with the colors today. Lie theory, it's not pronounced Lie theory. Something that I have talked about and will continue to talk about. Now, I can never fully give a course on Lie theory here. Well, I say that, who knows, maybe 1 to 3 years from now. Maybe I could, actually. But the thing is that this is something where you need probably at least 15 to 20 hours of basically graduate level lecturing. Okay, like let's see if I can bring it up. There's several. I mean, maybe I'll not talk about that right now, but there's one lecture series where that was the most helpful to me, and it was just like, so they'll do definition. Okay, they give us some definition, which is rather technical, complicated, and then proposition or theorem, or gonna say something. Usually they were propositions. I don't know what the distinction is between proposition and theorem. I think propositions are just kind of less important, but they're basically, the idea is we're saying something. We've defined something, now we're saying something, blah, 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 blah. And usually they would prove this or indicate, convince us why it should be true, why we should believe it, etc. And then after that, maybe lemma or whatever, they say more stuff, but maybe just another definition, and then proposition or theorem, and then definition, and just looping like this. And so each lecture was like an hour. This was on Lie theory, okay? And so Lie groups and Lie algebras. And they would do this, the professor, in this loop, and it just, like, if you put all these lectures together, you'd have like 20 hours. It's just 20 hours of this loop. Definition, proposition, definition, proposition, and it builds up, so it's extremely difficult to learn this subject. That's why it's a graduate level course typically. And now somewhere in here, it's really about the way I'll like really roughly explain what Lie theory is about. It's sort of about symmetries, but it's I would say it's sort of about rotation spaces. So some of the Lie groups out there, I mean, there's like 4 classical families of Lie algebras, I'll say, and there's 5 exceptional Lie algebras. You'll see me sort of using the word Lie algebra, Lie group interchangeably. They're not exactly 1-to-1, but they're almost 1-to-1. So that's another technicality. And another weird thing is that the theory was developed, speaking of complex. So they're typically, I believe they're semi-simple complex Lie groups and Lie algebras. Semi-simple complex. And these are technical terms. But this is where the theory was developed first, and it was sort of the first person to completely classify these was Élie Cartan. Élie Cartan, I believe there's an accent here. Sometimes on the with the accents on the capital letters, it's kind of skipped sometimes, but it's really there. Élie Cartan. So you can think of them as rotation spaces. So, for example, we have SO3. This is the special orthogonal group, which, if you think of in terms of matrices, the special means that the determinant is equal to 1. So what that means is that we're talking about matrices that are not really scaling the space. They're keeping, roughly speaking, they're keeping distances constant. So they're rotating, essentially. Now, if you just have the orthogonal group, this includes, for example, reflections. So a reflection will have a determinant of -1. It will, if you have some sort of chiral object, like a helix, okay, that is, suppose it's going around clockwise or something, like DNA, you know, a helix. If you then reflect it in a mirror, it will be rotating the other way. The chirality will be reversed. And so the orthogonal group, okay, the n represents how many dimensions. So, but the orthogonal group ON is where you have these, you allow for these reflections which have the determinant -1, whereas SON, okay, I'll just write SON, has this special means that it's +1. So we don't allow these reflections. It's basically, you think of these are rotations in Euclidean space, essentially. So SO3 is the rotations in 3 dimensions. You can look up the matrices. I mean, you can represent that with matrices in various ways. You know, in SO2, okay, the special orthogonal group of 2 dimensions, and we might specify that we're dealing with real numbers or complex, well, so you don't see that with SO. There's other groups like SL, where often we take the complex field of complex numbers. Okay, but we could also do SLR. Now, I'm not, SL is one of the, so this is special linear. Again, there's only like 4 of these families, 4 or 5. If you count, there's also GL, which is the general linear group. Sometimes, for some reason, it's not listed as one of the classical groups. Hold on, I gotta drink my coffee. So there's only like 4 of these. So I know this seems overwhelming or whatever, but there's not that many of them. Now, here I'm going to finish. So SO, I've always seen it just talking about the real numbers as a field, never complex, because complex will get you into other things. So there's SU, N, or SL. These are commonly done with the complex numbers. Now, this is always the complex numbers, so you don't need to specify. So you can have SL. You can have higher dimensionality of the special linear group as well, but SL2 in particular is very commonly studied. It has important connections and applications with number theory and modular forms. Modular forms, which I don't know too much about, and connected. In here also there's Mobius transformations are of interest, and if you look up the Wikipedia page for Mobius transformations, you'll see tons of discussions of these Lie groups. Now this one you can think of as, so if we're talking about, is it SU2 or SU3 that will be like the quaternions? I think it's SU2. And so this is sort of like the complex analog of the special orthogonal group. So it's basically, so SU2, so it's special unitary group. So it's describing matrices that are 2 by 2 with complex entries. However, it is unitary. So I didn't know I was going to talk about this today, so I wasn't prepared. I would normally prepare. The fact that it's unitary means that these off-diagonal elements will be complex conjugates or Hermitian conjugates. They're complex conjugates, okay? So right, like a B, the complement. And they need to add up to, so I think these can be different. Again, I'm not prepared, sorry. But special means that the determinant needs to be equal to 1. So we get this A times B minus C equals 1. That's based on how you calculate the determinant of a 2 by 2 matrix. So we get this formula. So let's see, this will check if I'm doing this correctly, because the dimensionality of SUN, so let's write it like this, I guess, meaning dimensionality of SUN is going to be equal to n squared minus 1. So for the number 2, this should be 3. Now each of these entries is a complex number, so we think of it as having 2 degrees of freedom. Okay. So we have A, B, and C, so that's 6 degrees of freedom. And yeah, I'm not prepared to talk about to explain all this stuff. I'm going off of memory stuff I studied a while ago. But anyway, this is going to be basically rotating vectors. If you have a 2-component vector in a complex vector space, so the entries here are complex, and basically this is, you know, it's very important in physics and in basic quantum mechanics. We have that's a whole other thing to explain, but that's what this is used for in physics, so it's very important. So we have the general linear group, which is, so that will be, for example, general linear of n and then some field. So you could, in generality, just write it like this. Sometimes you'll see it written down here, okay? And so it might be the real numbers, it could be the complex numbers, typically. It gets a little more complicated. There might be like exceptions and weird stuff going on, but some people do think about this for quaternions, which we denote with an H. But I'll just write for now GLN. It's the general linear group, meaning all the matrices, n by n matrices, that are invertible. So determinant not equal to 0. So yeah, that's a general linear group. We have special unitary, SU. We have special orthogonal, SO. We've talked about orthogonal, ON, and special linear. I might be missing one, I can't remember, but these are the sort of the classical Lie groups, okay? And if I write them lowercase, they become, so like SUN, then it becomes a Lie algebra. So you can write all of these as Lie algebras. Yeah, and so then these are also represented with diagrams called Dynkin diagrams. I don't even know why I'm talking about this. I just started talking about this and I'm stuck in the rabbit hole. So I was going to talk about something totally different, but let's just get through it. So you have these different graphs, for example, ADE, and called Dynkin diagrams, or there's, I think you can call it Coxeter diagrams, or Dynkin, Coxeter, Dynkin. There's a slight difference between the Coxeter diagrams and Dynkin diagrams, which I'll try to say later. But the type A graphs, okay, for example, just one dot is A1. If we continue it, this is A2 and A3. Okay, and then if we have it branching out at some point, this will be a D type graph. So type A, type D, and then type E is where if you extend this out, okay, what you end up with is two nodes on the left, and then you have this like T crossing or whatever, and then you have a number of nodes over here. So the first one is E6, and so total we'll have 6 nodes. So 1, 2, 3, 4, 5, 6 nodes. Okay, so E6 has this a lot of symmetry there, and the E diagrams just continue out. So I'm not going to write it out. E7, you just add another one. E8, add another one. Okay. And it actually goes up to E8. So you have E6, E7, E8, and you have type D. You would go extend out this way. So at the end, it has this thing. Actually, so we're skipping some letters. I forget if it's B or C, but I think it's maybe C. Yeah, C, I think, will go the other way. So like maybe this. So it doesn't really matter. The distinction between type C and type D is unimportant. So that's why we kind of skip it. And there's something similar with the type B diagrams. They exist, but I forget what they look like, and for some reason, for a similar kind of reason, we can ignore them, I think. And there's also, if you're interested in the geometry of it, there's H diagrams for Coxeter systems. However, for Lie groups and Lie algebras, there's no H. So what is all this about? Well, again, you have to do like a full course in Lie theory to properly explain this stuff. But this is how Lie groups and Lie algebras are classified, at least the complex semi-simple ones. And if I remember correctly, so I don't remember correctly. The A types are, I believe they correspond to SL and SU, and D. So then there's SO, the even SO groups, and then there's the odd SO groups, which I think we write like this. I forget. Anyway, I wasn't prepared to lecture on this. I'm just saying it's a deep, complicated subject, and so, but also this is used to describe Lie theory, but it's also used to describe Coxeter systems, which are all about, for example, you have the Platonic solids, which are in 3 dimensions, in higher dimensions, we call them regular polytopes. So these platonic solids have analogs in higher dimensions, and Coxeter studied this stuff a lot, and so you can think of it as the classification of these regular polytopes corresponds to this stuff. So there's a correspondence here. So it's really all about symmetry, but the Lie theory, it's not really about symmetry in terms of just reflecting things. At some point it does become about that, because you develop these things called root systems, root lattices, and there you do have this kind of symmetry. So that's kind of where it connects. But really, I kind of think of these as rotation spaces. It's asking, what kinds of rotations can you do with geometry? And so we have the obvious ones are the SON, and also the orthogonal group is somewhat obvious. But when you get to complex spaces, you have SUN and SLN. And then, actually, so that gives us an intriguing thought, because we start with sort of real numbers or complex numbers, but we start with sort of Euclidean geometry, the obvious geometries, and we get SON and ON. And then when we start thinking in terms of rotations on complex vector spaces, then we get SUN, SL2N, or SLN, sorry. So the way to sort of level that up, to expand on it, is to talk about the quaternions, and then also the octonions, and ask, can we go higher up? And actually, the quaternions show up in the SUN stuff. And then the octonions are where you get actually the exceptional Lie groups and exceptional Lie algebras. And the exceptional ones, so all of these, like SUN and ON and stuff, those are called the classical ones. And then the exceptional ones are, these are three of them. And then there's G2 and F4. So the reasons behind how these letters were chosen, I don't know for the Dinkin side of it. I don't know exactly the history. It's an interesting question. Was it Coxeter? Was it Dinkin? Actually, I think they both use similar ideas, because the history went back further than that. That people had started investigating some of this stuff, symmetries of regular polytopes and that kind of stuff, and representing them with graphs. So some theory already existed, and I think they both built off of that, but I could be wrong about the history. But so we have these other exceptional groups, and the Dinkin diagrams. For G2, it looks like this, 2 nodes. And then we have, I believe there's 3 connections. So these nodes can have more than one connection between them. And when they have that, they will be a Dinkin diagram. The Coxeter diagrams, I think they don't allow that. Now F4, let's see if I can remember what F4 looks like. Yeah, I think I remember it. So we'll have a node here, here. And then these ones right here have 2 edges connecting them. This is F4 and G2. Now, what was I going to say? Yeah, somewhere in here, when I was talking about this earlier, I kind of forgot about the whole having 2 edges connecting nodes. So that's where, somewhere in there is the B diagrams, I think they have... I think it's just... they have that double connection and then dot 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 over here. I think that's the type B. But anyway, so these... there's also this thing called Dinkin diagram folding, and of particular importance is this structure, which this is D4, because this is this type, but it's just with 4 nodes, so this will be D4. So you can imagine sort of folding this, smashing them together, and you get this. And this structure, once you have this structure, or alternatively, or this, okay, but this structure, and you can see it here as well, and you can see it here, okay? So once you have that structure somewhere in your diagram, you have what's called triality, which was developed, first thought of by Élie Cartan. I'll talk about it more in the future. It's very important, triality. And anyway, it's a deep subject. It's a deep subject. And to explain it properly takes quite a lot. Hours and hours and hours of lecture where it's like I described, definition, proposition, definition, proposition. It's very intense. And for me, the first few times I watched through series of lectures and tried to understand it, I didn't really understand it at all. So it took a few times. Finally, at one point, sorry about the noise in the background, nothing I can do about it. Finally, at one point I understood it. But with these kinds of very complicated things, what happens is you work really hard to understand it. You understand it once, and then the next day you think about it, and so like it was all pieced together in your head, like, I understand it. But you can't just keep that going. You have to come back to it again, because the next day you're like, wait, actually, some of it just fades, right? There's just this brief moment of clarity. Then it fades, and then you come back to it, which I haven't done yet. It was maybe 6 months ago or something. Finally, it felt like I understood it. Then I'll come back to it, because there's many things, like, for example, the whole story with root lattices. I couldn't even begin to explain how you get from Lie groups to root lattices, as an example. So when it's explained to me, I go, oh yeah, that's right, because I've seen this presentation a bunch of times now. So if somebody explains it to me, I'll be like, oh yeah, that's right, I remember now. But I cannot remember it at all. I kind of have a bad memory, to be honest. But so I'll go back, I'll review this stuff. Hold on. I'll review this stuff, make sense of it, and then I'll understand it a second time. And because this stuff is very hard, I might have to do this a few times, but eventually it will be, over time you become more and more fluent with it. Now the trouble I have right now is all of this stuff is the semi-simple complex Lie groups. Now the semi-simple, basically, it kind of means that it's nice. I think that it's connected or something like that. Don't worry too much about it. But I wonder, what about the real Lie groups and the real Lie algebras? Because I want to compare and contrast so that I can make sense of, like, yeah, normally you understand something in the real case first, but it turns out the classification is more complicated in the real case. There's these things called, I believe they're called Satake diagrams. And it's very hard to understand them because almost nobody's talking about them. And I have his book. It's very It's actually just lecture notes. It's very hard. I'm not sure that it even describes his diagrams. But so this treatment of the real Lie groups and the real Lie algebras is very hard to find. It's out there somewhere. They've been classified. But it's... I'll write this out. Location. Yeah, I would like to understand that. And then, by comparing and contrasting, be able to comment more. Because I would feel remiss trying to give presentations about the complex case when I don't understand the real case and I don't properly understand the differences between them. So it's a bit complicated. That's kind of where I'm at with it. But after a lot more work, maybe I will understand the classification of the real Lie groups, real Lie algebras, and so on. That would be nice. So all this is to say, I think the reason I started talking about Lie theory is just to say that this is a very important subject. It's of paramount importance in physics. If you listen to like Ed Witten talk, he's throwing around these Lie groups all the time. String theorists, people who do theories of everything, are, when you listen to them, they're talking about these things all the time. So they're very sort of foundational. But in terms of popular videos, there's basically none that are properly explaining it because it's just too hard to explain it in a popular manner, you see. By popular, I just mean for the average person. So it's quite a beast. So, but I will continue to talk about them and try to help people, because in the beginning, I didn't understand this stuff at all, and it was very confusing and difficult. I mean, I've never really seen a proper presentation where they just list out these groups, you know, SO, SU, SL, GL, just list them out and explain what they are. That was the first thing in Lie theory that I wanted to learn. Like, what is the meaning of these groups? How to think about them intuitively. And by the way, I mean, if you get to SU3, okay, SU3 now is basically if you had a vector with 3 components, so I'll just call them alpha, beta, gamma, but it's in a complex vector space. So each of these have, you know, like a plus bi. You could represent it like this: c plus di, e plus fi, right? And you're asking, what are the kinds of matrices? Basically, we'll draw an analogy to the, let's just do XYZ. This is in a real vector space. Typically, non-mathematicians, if we deal with vectors and matrices and vector spaces, we're almost always just doing it in a real vector space. We don't even bother to specify that. However, for mathematicians, it's probably different. And for physicists as well, different. But so we might talk about what are the 3x3 matrices we can put to the left here and manipulate this vector, for example, to rotate it. Imagine the surface of a sphere. You have a vector and you're rotating it around. It could be pointing over here now, you know, like a clock, but in 3D. I'm very bad at, drawing this stuff. This is a sphere, okay? And we can rotate this vector in various ways, right? This will be SO3 when we refer to it as a Lie group. So you can use a few matrices. There's different ways of doing it. But, or you could even use quaternions. Okay. But you sort of think, I want to form some kind of basis in this space of rotations. That's really what Lie theory is about. What matrices can I use to form a kind of basis? And typically, we put these matrices, we exponentiate them. So it'll be some amount of this, which I'll just call A, I guess. And some amount of this other matrix, and some amount of another matrix. This story of rotating in 3 dimensions has 3 degrees of freedom. Pilots refer to this as pitch, yaw, and roll. So if you want to look that up and think about it, go ahead. But you need 3 degrees of freedom. Now you might think, well, okay, there's 3 dimensions, so we need 3 degrees of freedom. Well, that's not how it works. In 2 dimensions, if you have a flat piece of paper, you can rotate it this way or this way, but that's the same degree of freedom, just positive and negative. So it has 1 degree of freedom in 2 dimensions. In 4 dimensions, it will have 6 degrees of freedom. The way that works, you have a matrix, say it's a 4 by 4, for example. I'm just going to write the identity matrix to start. It's how many of these positions that you have. So here you have 6. And it's in general going to be what? N squared. What's the formula? Oh, it's n choose 2. Sorry. That's really the way to think of it, I guess, is n choose 2. So for each, like, you have x, y, z, w, you can rotate between x and y, you can rotate between x and z, x and w, y and z, y and w, w and z. You get this kind of situation, which is n choose 2 kind of situation. Anyway. So in 3 dimensions, we have 3 degrees of freedom, and I've talked before about this Lie theory stuff, about the whole exponentiating a matrix and how that works. So you can look that up for other videos that I've done. But, so we ask ourselves the same question for the complex case. What kind of rotations can we do? And that's where you, in the 3 complex dimensional case, you get SU3. And it turns out that this describes the structure of the strong force. So that's very interesting. So that's what we find. We find that the forces of nature, other than gravity, can be described with these Lie groups. So that's sort of how modern physicists, a lot of them think about it, is they think of all the laws of particle physics. So all of physics minus gravity, other than gravity, okay, is these Lie groups. U1, I'll explain what the U1 is, because we didn't say that. Cross, this is called a direct product. It works, it deserves some explanation, but it works the way you'd think it would work. Cross SU2, cross SU3. This is what physicists use to describe all of particle physics. And this is the really complicated one. This is the strong force. So when I wanted to learn this stuff, I spent a lot of time just trying to understand how to think about this group intuitively. And some people, they just don't care. They're like, well, it's described by these matrices. You know, if you ever needed to do a computation, you use these matrices, and they're satisfied. But I'm thinking about what's physical, what is honestly, what is really happening. So there was a lot of stuff to think about. But I've never seen a proper presentation where they just go through all of these and explain what these Lie groups, what they mean or what they correspond to. Yeah. By the way, so it turns out that the SU1 and U1 are the same, so that's why we just write U1. And yeah, so I've never seen a proper... So the way it's usually presented is to explain all of Lie theory, and that ends... Typically, these sort of culminates with the full classification of Lie algebras, these semi-simple complex Lie algebras using Dynkin diagrams. And along the way, they never really explained, well, I mean, usually they kind of do. They do explain, like, what SON is, what SUN is, SLN. But I was just never satisfied. I had to go around to many, many different sources, just picking up the pieces and trying to figure out what these different things are. And the SLN case remains, it's a lot of things. So it remains a little confusing for me, a little mysterious. There's just a lot of things to say about SLN. So that's... And I guess also going to higher dimensions of SUN, beyond 3 dimensions, also, I would say I could probably spend a lot of time trying to sort of come up with an intuitive mental model for what that involves, but I haven't spent much time on it, so maybe someday. So all of that is just to say that this stuff is very complicated, but also very important. Now, will I ever be able to give a full, like, series of lessons explaining the theory from top to bottom in a good order? I don't know if I'll ever be able to, but it won't be anytime soon. At least a year or a few from now. But that's... I think we need more people talking about this. And this is just one example. There's many, many other examples where this really beautiful and important mathematics is partly because it's difficult. It's not talked about as much as it should be. That's probably the main reason, honestly. But I just want to be another voice talking about it. And I have potentially some original results. I guess that's another discussion for another time. But I have a lot more I wanted to say. This whole thing was just a sidetrack. But I guess the point is that I'm going to be rambling. Kind of like I did here today. And why? I don't know. I mean, like triality, for example. It's kind of on my to-do list to talk about it. What Elie Carton talked about with triality. There's a lot to say there. I guess it's the beauty of the math. I want to communicate it. I want to share it. So there'll be more stuff, but it's going to be rambly. But over time, I'll be able to do better treatments. I mean, recently I did this video on differential geometry. So where is that? Differential geometry, this one. And somewhat well received, I think, as far as my channel goes. And basically, this topic, I think it did well because it's got a good thumbnail and a good name, differential geometry. If I did a very similar thing with linear algebra, I think the phrase linear algebra just isn't going to attract as much attention. It kind of sounds boring. And to be fair, linear algebra sometimes is a bit boring. It's sometimes very interesting, sometimes a bit boring. Let's be honest about it. It can be boring. Differential geometry is exciting. It is. So, but I did this talk, hour and 15 minutes. And at the end I was like thinking to myself, well, maybe some people would criticize that this wasn't really about... I felt like maybe it wasn't really about differential geometry. I was sort of just whetting the appetite and talking about what are probably sort of prerequisite ideas, but anyway, sort of things that came before. But then after making this, I checked the Wikipedia article for differential geometry, and it was almost like as if I had used the Wikipedia article as like a outline for this video. It was, so I was like, wow, it's actually, I kind of was dead on with the material, in my opinion. And I mean, that just happens because I've spent a lot of time learning differential geometry from many sources, so that was the result. So I'm happy with that. It was, it's an introduction. It's not meant to be presenting the material from the ground up, really. I didn't even give a proper definition of what differential geometry is. It's a very broad topic, so that actually might be a little hard to define, to be fair. Yeah, so there's going to be some of this content, but I'm also going to do the Roblox content. I guess the secret idea, it's not secret if I'm telling everyone, but kind of maybe the idea of this channel is going to be sort of like luring in young people with silly Roblox content and then shoving advanced math in their face. But I think that if I were just doing math, I wouldn't believe in what I'm doing, that it would have potential to succeed. For various reasons. And I don't want to only do Roblox because I'm 37 and that would be a bit cringe. Now, I don't know if young people realize this, but for older people, maybe like 18 and over, Roblox is considered cringe and for kids. But that's okay. I mean, there's nothing wrong with... let me put it this way. I try to judge things regardless of what kind of stigma or stereotype something has. So, judge it for myself. So, Roblox is a piece of technology, a platform. And actually, building things is very interesting. Admittedly, playing the games is almost always uninteresting to me. There's some moments, it has its moments, but it's pretty uninteresting. But building things is interesting to me. So it's like Legos or something like that, It's appealing. So I guess that's the plan. Yeah, I'm having trouble thinking because of the noise. It just feels weird making this video with the noise in the background. So I'm probably gonna redo this video again. But I'm gonna upload this anyway because I went on this ramble about Lie theory, and I'll do that again a few times at least. There's also this whole topic of how these are related to RCHO, which is the reals, complex, quaternions, octonions, and I've barely even talked about this forms a pattern. After that you have the Sedenians, but the Sedenians usually aren't mentioned. There's a reason for that. Blah, blah, blah. There's a lot to talk about here. There's even people trying to do unification physics with the Sedenians, which is interesting. So there's just a lot to talk about. And you can view the whole story of Lie groups and Lie algebras in these terms and say, this is why it's these specific, it gives you this question, why these Lie groups? Well, of course, that's kind of what the classification theory is about. We find all the possible ones and prove that there are no more. However, in a more intuitively satisfying manner, we can explain them with this. That's a whole other can of worms. Stay tuned. Leave a like if you enjoy my content. See you next time. Bye.